Welcome to the Crazy Hat Chemist. So here we go, another paper and pencil, or rather paper and pen example of a stoichiometry worksheet number 2. You can see that title right up here. And just like always with all these videos, I'm assuming you have done a number of things prior to attempting this worksheet. Number one, you've watched my videos and done the worksheets associated with nomenclature. You have your ions and charges memorized. You have your periodic trends known. Number two, you have watched my videos on chemical reactions and you understand the basics of all chemical reactions as well as balancing and the 5 different types of chemical reactions. Number three, you have watched my videos on stoichiometry. And so you're familiar with the background on that. You should also have out with you a periodic table. And this is the periodic table of which we are using here. This is from the SAT subject test in chemistry a long time ago. And in addition to that, you should also be familiar with this flow chart right here, and that would be essential as well. I'll be referring back to that periodic table and this flow chart frequently throughout this video. So we're going to get right into it. This is stoichiometry worksheet number 2. I'm also assuming that you have done already previously stoichiometry worksheet number 1. You do need to use the periodic table of which I have, otherwise your molar mass determinations will be incorrect. So make sure that you are doing that. All right, so let's get right into it. If you do like this video, like the other ones, please give me a thumbs up and please subscribe to my YouTube channel. I would greatly appreciate that. That encourages me to make more of these crazy videos trying to help out students in chemistry. So I greatly appreciate that in advance if you subscribe to my YouTube channel and also give me a thumbs up. Lets me know that you like this. All right, so here we go. Without further ado, let's attempt to do number 1 on stoichiometry worksheet number 2. Here we go. It says calcium metal is placed in a beaker of 0.56 grams of cool water. How many liters of gaseous product at STP is produced? All right, so calcium metal, that is Ca, and that is a solid because calcium is an element. In its standard state, calcium is a solid at standard conditions, so that's why that's a solid. Right? And then it in a beaker of cool water. So it doesn't matter actually if it's hot water or cool water, but in this particular case, it does help the reaction proceed faster. That's why it's cool water. Not that that really matters. We could actually cross off the cool water and we can just write the formula for water. Now, most students are going to write the formula for water as H2O, but I highly recommend, and if you follow my chemical reactions videos, and worksheets associated with that. If you write water on the reactant side, please write it as HOH, okay? It is a liquid. And this is the type of reaction in which this is a single displacement type of reaction. Okay, and the reason that we're writing this as HOH is so that you can clearly identify the cation and the anion. I have underlined the cation with a solid line, that's the hydrogen, and squiggled the anion, which is hydroxide. And since this is a single displacement or a single replacement reaction, the calcium metal is a metal and it forms cations. So it will displace one of its own kind. That is, it will displace either a metal or a cation. There are no metals in water, but there is most certainly a cation in water. So calcium is going to displace the hydrogen, and then we are going to get hydrogen by itself. Now, when hydrogen is by itself, it is a diatomic. So that is going to be H2. That's why that's 2. Hydrogen is a gas at standard conditions. So that's its state of matter. Plus. And now what we need to do is come up with the other product. And this is characteristic of all single displacement reactions. We have an element and a California. And what will be produced is an element and another California. The California is a cation anion combination, that is. So as you can see, the hydrogen has been removed by the calcium because it displaces it and you get hydrogen gas. What remains is hydroxide. So calcium, if we go back to our periodic table, here is calcium. And calcium is in group 2, so it's predicted to have a 2+ charge on its ion state. So calcium ion and hydroxide are going to get together and form calcium hydroxide. So calcium is a group 2 + 2 and then hydroxide. And then the other thing I'm going to do is I'm going to highlight this really in a new color, and this is blue. And this requires parentheses because we have well, simply, we have more than one of this polyatomic ion. Most students, if they don't write water as HOH, they will get calcium oxide as the other product, but the other product is actually calcium hydroxide, and this is aqueous. Calcium hydroxide is slightly soluble, but it just happens to be rather soluble in this basic solution. It's one of the group 2 hydroxides, which is a strong base. Okay, now what we need to do is balance this reaction. And so there are 2 oxygens that you see here, and then I'm going to place a 2 right here in front of the water. And that will take care of the 4 hydrogens on this reactant side. 2 + 2, that's 4 hydrogens on the product side, 1 calcium, 1 calcium. So now my equation is balanced. All right, now what we're going to do is we're going to start off by finding the number of which we have, which is 0.56, and then the units, that's grams, and then the formula, and that is water. So we're going to actually start off with that. So it's 0.56 grams of H2O. So that's what we're going to start off with right there. And now what we're going to do is we're going to look at our flow chart and figure out what we want to do. So we're going to reread the question, and it says how many liters of gaseous product at STP is produced. So we got to figure out which of the products is the gaseous product. And the gaseous product, hopefully you see that because I've actually included the states of matter. The gaseous product is hydrogen gas. So that's what we need to go to. So we need to take our number here from water and go to the hydrogen, which is a gas. That requires a relationship to go back and forth with stoichiometry. So what we're going to do here is we're going to draw a line here, and we're going to kind of follow this along here. So here we go. So whatever units are in this numerator term, those same units need to be in the denominator of this next term. That would be grams, and then the same formula, that's H2O. So therefore, this is H2O here like this, okay? And then if I look at my flow chart, I am starting off with a mass, and there's only one thing I can go to from mass, which is grams. There's only one thing I can go to from mass, which is grams, and that is moles. And that is using the molar mass. So this tells me, going from mass to moles, it tells me what units are in the numerator. So what units are in the numerator is moles. So I'm going to have moles in the numerator and the same formula, H2O. And then I'm going to go back to my flow chart right over here. And what's the number in front of the mole? It's a 1. So a 1 in front of the mole. So this is a 1 in front of the mole. Okay, and the number in front of the grams outside of the starting number, which is right here, the mass, is using the molar mass. So what I have to do is pull out my periodic table, and I am going to find hydrogen, and its molar mass is 1.0079. I'm going to multiply that by 2. And then I'm going to take the molar mass for oxygen, that's 16.00. I'm going to multiply that by 1. I'm going to sum up those 2 numbers, and then I'm going to round to the fewest number of decimal places. Hydrogen has 4 decimal places. Oxygen has 2. So my rounded answer for my molar mass for water will have 2 decimal places, and that's 18.02 grams. All right. So now I have the ability to cancel out the grams of water. If I were to end right here, I would be solving for the moles of water, but I'm actually not ending here. So I'm going to continue this process here. So we'll draw a line. Now, whatever these units and formula are, in this numerator term, I'm going to replicate and duplicate those units and formula in this next denominator term. So that's moles of H2O. Okay. Excuse me. So I'm actually right here at this portion here of my flow chart. And now what I'm going to do is go up. I'm going to use a mole ratio. That mole ratio will allow me to change formulas. So I'm going to use a mole ratio, therefore moles. Now the question is starting off with grams of water, and then what do I want? I want the gaseous product. The gaseous product is hydrogen. So I'm going to go to the hydrogen. Draw a line here in the sand to separate that set there. And now what I need to do is I need to use the stoichiometric coefficients that are associated with these formulas on the balanced equation. So the stoichiometric coefficient for calcium is 1, for water is 2, for hydrogen is 1, for calcium hydroxide is 1. For this particular one, moles of water is going to be 2. So that's a 2 stoichiometric coefficient, and that for hydrogen is a 1, so this is a 1. So these two red numbers here are coming from the stoichiometric coefficients on the balanced equation. All right, now this enables me to cancel out the moles of water from the numerator to denominator. And I'm not quite done because I want to get to the units of which the question is asking, and it's asking for liters of this gaseous product. So whatever these units are right here in the numerator, those same units need to be in the denominator of the next term. So that's moles of H2. We'll continue this line just a little bit more. And so now we're going to go back to our flow chart and we're going to find out where are we. So we did a mole ratio. So now we drop down right back over to here. Some people would call this mole island. Okay, but right here, we are right here at moles. So from moles, we can go to mass of that gaseous product. We can go to molecules of that gaseous product, or we can go to volume in terms of liters of that gaseous product at STP conditions. So this only works at standard temperature and pressure. That is 1 mole is equal to a volume of 22.414 liters. So we have 1 mole is equal to a volume that's in liters. This is going to be hydrogen. Notice I'm not changing the formula again. The only time I can change the formula is when I have this mole ratio. So the number in front of the liters is 22.414. All right. Now, I am going to look at my significant figures of which I have on this problem. Leading zeros do not count, non-zero integers count. So this is 2 significant figures in this. This is a definition that is 1 mole is equal to the molar mass. So that's why this one is an infinite number of significant figures. And this molar mass has 4 significant figures, even though it has 2 decimals. This number 2 in the stoichiometric coefficient is an infinite number of significant figures. Same with this 1 infinite number of significant figures. This is a definition at 1 mole is equal to a certain volume at STP conditions. So that's an infinite number of significant figures. And this is a rounded number of which I have given it 22.414. That is 5 significant figures. So the fewest number of significant figures in this problem is actually the beginning number, and that is 2 significant figures. So what you have to do now is you're going to take your calculator and you're going to take 0.56 times 1 times 1 times 22.414 divided by 18.02 divided by 2 and divided by 1. And then from there, you're going to get the following number, and I am going to round this for you, and that will be 0.35. And the units are liters, and the formula is H2. And there's our number, units, and formula. That's NUF. Number, units, formula. Enough of that. We're done with that problem. By the way, when you are plugging this into your calculator, an alternate method here is to just go one step at a time and also ignoring the ones. Hopefully you understand that a number times one is that number and a number divided by one is that number. So you could take 0.56 divided by 18.02 divided by 2 times 22.414. That will end up being the same numeric value here after two significant figure rounding at 0.35 and liters of H2. All right, so that's problem number one. Hopefully you got that nailed. And we're going to keep on going to problem number two. So I'm going to scoot this on up here and we'll go to number two. Little quick advertisement, and that is you are watching the Crazy Hat Chemist. And please subscribe to my YouTube channel if you find this informative and you're learning something. So hopefully you are learning something. That's the whole point of all this. All right, so this next one, we have 1.68 grams of plumbous nitrate. So let me slide this down just slightly so we can write a couple of things at the top. Plumbous is a 2+ charge. Nitrate is a polyatomic ion, that is NO3 minus 1. So 1.68 grams of this compound is added into a test tube with potassium iodide. Potassium is a group 1, so it's a 1+ charge. Iodide is a halide ion, halogen, that is, at -1. Okay, and then so what we're going to do is we're going to write the reactants of this reaction, and then we're going to figure out the type of reaction, and then we'll carry on with the rest of the question here. So we're going to write out plumbous nitrate. State of matter of this is aqueous because all nitrates are aqueous no matter what they are with, so that's not a problem. And then we have potassium iodide. And chlorides, bromides, and iodides are soluble except for silver, mercury, and lead, or potassium, that's a group 1, and they're soluble, so that's aqueous. What you should recognize at this point in time is that this is actually a double displacement or double replacement reaction. So it's a double displacement or double replacement reaction. So you can see that I combined these two here to come up with the reactants, these two to come up with the other set of reactants. To come up with the products, I'm going to take this cation and combine it with the other alternate anion, and then this cation and combine it with the other alternate anion. And it doesn't matter which one you write first, which one you write second. On the product side, it doesn't really matter. So I'm going to write the, I'm going to combine the potassium and the nitrate together. So that's KNO3. And again, all nitrates are aqueous, so that's not a problem right there. And then I will have plumbous iodide. Plumbous iodide, that's Pb and I and 2. Plumbous iodide is an insoluble precipitate. And that is, the rule is iodides, chlorides, bromides, and iodides are aqueous except for silver, mercurous, and plumbous. So this is one of the exceptions. All right, now what we need to do is balance this equation here. And it looks like I have 2 iodines, I have 2 nitrogens. So there's 1 iodine here, and so I'm going to place a 2 in front of the potassium iodide. And then I said that there are 2 nitrogens, and there's 1 nitrogen, so I'm going to place a 2 in front of the potassium nitrate. And now this is balanced. You should check that all the other elements are balanced, but it is. All the other elements are balanced at this point. All right, now what we're going to do is we're going to start off with our number, units, and formula on this problem. So I'm going to pull out my ruler so that we can start this off and it looks pretty and nice. Okay, and we are going to start off with a number, units, and a formula. That number is 1.68. The units are grams, and the formula is plumbous nitrate. So that's what we're starting off with on this problem here. Now what we're going to do is we are going to read the rest of the question, which I hadn't read yet, and find out what it is that we're actually solving for. So it says, how many moles of nitrate compound is formed? So that means since it is a nitrate compound formed, that means it must be on the product side. So I am not looking at this reactant side, I am looking at the product side. I'm going to find on the product side which one of the products is a nitrate compound, and that is this whole thing right there. It says nitrate compound, so I'm not looking just for the nitrate, I am looking for the compound with nitrate. All right. So I am starting off with plumbous nitrate. I need to go to the nitrate compound on the product side. And the only way to do that is through a mole ratio. All right. So let's continue on with this here and figure out what we need to do. Okay, this is a really simple process of dimensional analysis, unit analysis, and canceling units. That's what we're doing here. Step by step. This is grams of plumbous nitrate. That means that this must be grams of plumbous nitrate in the denominator. And we will draw our little line over here to separate all our terms. Okay, so we're going to put our flow chart, and our flow chart says that, well, we have mass, which is grams, and there's only one thing we can go to, and that is moles. We are going to use the molar mass to go from mass to moles. Okay, so moles is my numerator term. So I'm going to have moles of the same formula, that's plumbous nitrate. And now we need to figure out the numbers that are associated with these units. So the numbers go hand in hand with the units. So the number in front of the mole is a 1. So we're going to place that right there like that. The number in front of the mole is a 1. And then the molar mass, that is actually a gram value. And we're going to get the molar mass for plumbous nitrate. So what we need to do is pull out our periodic table, and we need to find 3 elements. One of them is lead, that is right here. Its molar mass is 207.2. Then we need to find nitrogen, and that's right here, and its molar mass is 14.007. And then we need to find the oxygen, and that's right here, and that is 16.00. So if we flip this over, we're going to look at this formula here, and we are going to use 1 lead. So we're going to take this molar mass of 207.2 times 1 plus nitrogens. How many nitrogens do we have? 2 of them, because this 2 distributes over all these parentheses term here. So there's 2 nitrogens. So we're going to take 14.007 times 2 plus 2 times 3, that's 6 oxygens. So that would be 16.00 times 6. Okay, and then I add up all those values, and then I round it to the fewest number of decimal places. Nitrogen has 3, oxygen has 2, lead has 1. So the fewest number of decimal places is with the lead. So our molar mass rounded correctly is going to have 1 decimal place. So it's going to be 333.2 grams. So I think I said this on the first video, but I'm going to reiterate it on this video here, and that is I highly recommend that you calculate a whole number molar mass after you have calculated the rounded one. Okay, this is one of the most common errors and to get the wrong answer of the problem. So what you're going to do is make sure that your formula is correct. You're going to have 1 lead. So I'm going to take the molar mass of lead and take a whole number. So that's going to be 207 plus 14 times 2, that's 28, plus 16 times 6, it's what, 96. So I'm going to add all that up. Is that close to the 333? The answer is yes. If it is true, that's a yes. Then you can continue on with the problem. All right, so what I've done is I'm going to cancel out my grams of plumbous nitrate. Now, this is moles of plumbous nitrate here in this numerator term. Consequently, moles of that same formula, plumbous nitrate, needs to go in the denominator of this next term right here. Now is my opportunity to change formulas, and I can change formulas using a mole ratio. So I'm going to have a mole ratio, that's a ratio of moles, and I can have any formula within this balanced equation I want. I happen to go for the nitrate product, which is potassium nitrate. So I'm going to write that right there like that. Okay. I'm going to draw a line here signaling that that stage is almost done. And now what I need to do is use the stoichiometric coefficients from the balanced equation to place in front of the mole values. So lead nitrate, that's plumbous nitrate, is right here. It has a coefficient of a 1, so that's why this is a 1. Potassium nitrate has a coefficient of a 2, so that's why this is a 2. I'm going to be able to cancel out the moles of plumbous nitrate, and well, I have still one more step to do because it says how many, oh wait, no, I don't. It says how many moles of the nitrate compound. I'm actually done. So this is going to be an equal right here because I have moles of the nitrate compound. Fantastic. So I'm going to look at significant figures. This first number here has 3 significant figures. Then this is a definition, infinite. This has 4 significant figures. And these are both definitions here, counting numbers, if you will. These are counting numbers, so those are infinite. Okay, so my least number of significant figures here is 3. In my calculator, what am I going to do? I'm going to plug in the number 1.68. Then I'm going to divide by 333.2. Then I'm going to multiply by 2. And then I'm going to round that number to 3 significant figures. Okay. I have written this number, or I'm going to write this number in exponential notation. It could be in decimal form. It really doesn't matter. But I have 1.01 times 10 to the negative 2. That's in decimal, that's in exponential notation. It doesn't really matter. That number needs units. Those units are moles. And it needs a formula, and that is KNO3, potassium nitrate. So I have number, units, and a formula. Enough of that. All right, so hopefully you are okay with that problem and you're quite happy how that one went. Okay, just please reflect back on everything on that one. All right, another little sip of water before we carry on with our next journey here. And we're going to do problem number 3. And so I'm going to slide this up here so that you can clearly see problem number 3. All right, here we go. Boom. Yep. Okay. Again, quick little advertisement gig, and that is I am the Crazy Hat Chemist, and hopefully you're getting a lot of these videos. Please subscribe to my YouTube channel, and please give me a thumbs up on this video, and give me give me some comments. I'm here for you. I'm here for your chemistry learning, so you can do well in whatever career you want that involves chemistry. Here we go. So our next problem here is number 3, and it says naphthalene C10H8 mothballs. So I don't know if you have a elder relative in your family, maybe a grandparent or something like that, but they might have some wool blankets or wool sweaters or something like that. And mothballs are to prevent moths from eating up their wool materials, those natural fibers. Okay, it is pretty toxic. It's pretty potent stuff. So I'm sure you would recognize its smell if you were to smell it. So it says that I have naphthalene. Good thing we got the formula for it. Naphthalene, they're mothballs. They're actually physical round white things, and they put them in these like bags with holes in them. So they're actually a solid. Okay, and it says it's burned in a crucible. It doesn't really matter what the container is, but the key word is that it's burned. So that lets us know that this is a combustion reaction. So what we're going to do is we're going to have our naphthalene C10 H8, and that is a solid plus. So all combustion reactions require oxygen, and that's molecular oxygen, so that's O2. And that is a gas at standard conditions. So those are my two reactants. We're going to draw an arrow. We're going to put a delta above an arrow because combustion reactions require a kick in order for that reaction to proceed forwards, like a spark, a lit match, or a Bunsen burner, or something like that, a striker for a Bunsen burner. Okay. And in a complete combustion, you're going to get the following: carbon dioxide, that is a gas, and water. And more than likely, that's going to be a liquid. All right. So this is a combustion type of reaction, as the keyword burned would suggest. And that's why I have the reactant of oxygen and the products of carbon dioxide and water. Those are characteristic of a combustion type of reaction. So now what we need to do is balance this, and this will always be balanced combustion reactions in the following order. First carbons, then hydrogens, then finally oxygens. So carbons, I have 10 on the reactant side. I'm going to place a 10 in front of that CO2. I have 8 hydrogens here. I have 2 over here. So this requires a 4. And so now we're going to count up the number of oxygens here. That's 10 times 2, that's 20. And then 4 times 1, that's 4. I'm going to add that up. That will equal 24 oxygens. So therefore, I already have 2 here. I don't have any oxygens in the naphthalene. And so I'm going to have 12 as my coefficient in front of the oxygen. And now it's balanced. So I didn't have to use a fractional coefficient for once. Yay, finally. All right. So we're going to now continue to read on this problem and figure out what we need to do. That's when 3.15 grams of gas reacts. So what's the gas that reacts? That's actually oxygen. So I'm going to start off with that. 3.15 grams of gas. That's the O2 that reacts. So I'm going to start off with that. I'm going to draw my line here to differentiate where I'm starting, where I'm going, what I need to do. And I'll draw this vertical line here so that I keep all my order together. Okay. It says when 3.15 grams of gas reacts with the mothballs, how many grams of liquid product will be formed? So which one of these two products is the liquid? This one is the liquid. So I am actually going to the water. So I'm starting off with the oxygen and I need to go to the water. All right. Fantastic. So hopefully that concept made sense for you. So now what we need to do is we're going to have grams of O2 here. So whatever these units and formula are in this numerator term, I'm going to mimic those same units and formula in the denominator term. Okay, and so this is grams. Just like before, we have our flow chart. We're going to start off with a mass, which is grams. I'm going to go to moles. I'm going to use the molar mass to go from mass to moles. The molar mass is grams. I'm going to get that from my periodic table. And then the number of moles would be 1. Okay. So this is moles of the same formula. That's O2. The number of moles is a 1. And then I need to look up on my periodic table and I need to find oxygen. And then here we go. Let's find it. There is oxygen and the molar mass for O is 16.00. But I need to multiply it by 2 because the formula is O2. So that would be 32.00. I'm maintaining the fewest number of decimal places, which is 2. This will enable me to cancel out the grams of O2, just like that. Fantastic. All right. So now what we need to do is we need to convert the moles of oxygen into the moles of whatever compound I want, which is the liquid product, and that is water. So I'm going to have moles of O2 here in this denominator term. That way they cancel out. And I'm going to use this mole ratio to change the formula. Again, the mole ratio is the only way that you can change the formula. Okay. And so I'm going to use the stoichiometric coefficients associated with these from my balanced equation. So for O2, I have a 12, so this is 12. For the water, I have a 4, so this is a 4. You only use the stoichiometric coefficients one time within a problem. Notice also that the molar mass is 32.00. It is not 32.00 times 12. That would be incorrect. It is 1 mole is equal to the molar mass of that formula. Okay, all right. All right, so this will enable me to cancel out moles of O2 just like this. Now, I have just now changed the formula from O2 to H2O, and now it says that I want grams of this product. So I have one more step to do. So whatever units and formula are in this numerator term, that is moles of H2O, need to be in this denominator term. I'm going to go to a mass. So I'm pulling out my flow chart and I'm going to go from moles to mass. I'm going to use the molar mass. What's the number in front of the mole? It's a 1. I'm going to use the molar mass for that compound. So grams and then H2O. And then the number in front of the moles is a 1, and the number in front of the grams is going to be the molar mass. And this is the second time that we have calculated the molar mass for water within this one worksheet. And the first time was on problem 1. And recall that our molar mass for hydrogen is 1.0079. I'm going to multiply that by 2. That for oxygen is 16.00. I'm going to multiply that by 1, summing those numbers up, and then rounding it to the fewest number of decimal places, which is 2. So this will be 18.02. Then I can cancel out the moles of H2O, just like that. All right, so now in my calculator, what I'm going to do is I'm going to take 3.15 divided by 32 times 4 divided by 12 times 18.02. And I will get a numeric value. And then I'm going to round it. How do I round it? I'm going to look at significant figures, 3 significant figures for this 3.15, infinite for the definition of the 1 mole. 4 for this value right here, infinite for this counting number, infinite for this counting number, infinite for this definition, and 4 for that number. So the fewest number of significant figures I have on this problem is 3. So I'm going to get a calculator number, and then I'm going to round that number to 3 significant figures. The number is 0.591 grams of H2O, and that is my number, units, and formula on that problem right there. Okay, hopefully everybody's okay with that, and we're doing well. So, all right, we've done 3 of the problems here on the worksheet. So I'm going to peel this sheet of paper away, and now what we're going to do is go on to the 4th problem here. 4th problem, let me reorganize my little bits of paper here. All right, so let's get this in focus here. Focus, hocus pocus. There we go, now it's focused. Again, quick little advertising blip. If you're enjoying these videos, please subscribe to my YouTube channel. Give me a thumbs up. I'd greatly appreciate that. All right, here we go. Our next problem here, it says sulfuric acid is added to sodium hydroxide. So sulfuric acid is added to sodium hydroxide. The reaction produces heat and other products. So the first thing we're going to do is write a balanced equation. So sulfuric acid is, it does not say hydrosulfuric. So sulfuric acid is coming from the sulfate ion, and that's what that is, SO4 2-. All acids have a hydrogen. Sodium is a group 1, so that's 1+, and hydroxide is a polyatomic ion as 1-. So that's how I'm going to come up with my formulas. So I'm going to have H2SO4, that is aqueous like all acids, plus NaOH, and this is going to be aqueous because it's a group 1 hydroxide. This is characteristic of a double displacement reaction. So that means that my products is going to be combining the hydrogen with the hydroxide as one product and the sulfate and the sodium as the other product. And it doesn't matter which one we write first, which one we write second, provided that we have the correct formulas. So hydrogen and hydroxide, that's actually going to be H2O. That's a liquid. And then we have sodium sulfate. That's Na2. SO4, it has a group 1, that's a sodium, and therefore that's aqueous, like that. Then we need to balance this over here. We've got 2 sodiums on this product side. We're going to place 2 sodiums on the reactant side. And now we have 4 hydrogens on this reactant side, and we need 4 hydrogens on this product side. You should double check to make sure that everything else is balanced, but it is. I guarantee it. All right, so now what we're going to do, I'm going to do something a little bit different on this problem because this is a very complicated problem, requires quite a bit of stuff. So it says we have 12 mils of sulfuric acid. So we have 12 mils of sulfuric acid, and there's a density to this that's 1.84 grams per mil. And then we have a 13.5 grams of sodium hydroxide. And then it says how much salt is produced. So produced, that would be either the water or the sodium sulfate. And which one is the salt? This is the salt. So I'm going to end up going to the sodium sulfate. So this is a very important concept here because this on this problem is a limiting reagent or a limiting reactant type of problem. And the reason I understand that and know that is because I have numbers for both reactants. Notice that the other 3 problems of which I had, I only had one number for one of the reactants. Therefore, the other reactant was an excess. So this one here, since I have numbers for both reactants, it's a limiting reagent problem. It requires a lot more work. It's a little bit tedious, but it's not any more difficult. So that's the key part, that it's not any more difficult. All right, so we're going to start off with this 13.5 grams of sodium hydroxide. Okay, so we're going to say 13.5 grams of NaOH right there like that. Let's start off with that one. Perfect. So that is my starting material. And what do I want to go to? Well, I need to take this 13.5 grams of sodium hydroxide and I need to convert it to the salt. The salt is the sodium sulfate here on the product side. This is grams of NaOH. I'm going to have grams of NaOH in the denominator such that I can cancel units. I am going to this flow chart and I am going from mass to moles. Okay, I'm using the molar mass to convert from mass to moles. I'm going to have 1 in front of the mole. Okay, so I'm going to go from mass to moles of the same formula, NaOH. Draw a line right over here so I can differentiate that. The number in front of the mole is a 1, and then the number here in front of the mass is the molar mass. So I'm going to find sodium on my periodic table. That is right here. The molar mass of that is 22.99. The molar mass of hydrogen is 1.0079. And then the molar mass of oxygen is 16.00. I'm going to sum up those 3 numbers. I don't need to do any multiplication because there's only 1 of each. And then I'm going to round it to the fewest number of decimal places, which is 2. So 40.00 will be my molar mass for sodium hydroxide. That will enable me to cancel out the grams of the sodium hydroxide. Ultimately, I need to get a mass of this product that is a salt, so I need to keep on going. All right, so this is moles of NaOH. This must be moles of NaOH here. Okay, And then I need to go from moles of NaOH to the sodium sulfate. And this is when I'm going to use a mole ratio. So Na2SO4. So I'm using a mole ratio. And so with a mole ratio, I can change the formula as you can see here. I've changed the formula. It's a mole ratio. I'm going to use the stoichiometric coefficients from the balanced equation. That's a 2 in front of the sodium hydroxide. It's a 2, and a 1 in front of the sodium sulfate. That's a 1. Okay, this will enable me to cancel out the moles of sodium hydroxide, like thus. Then I have moles of sodium sulfate here, and I'm trying to get to grams. So I have one more step here. So I'm going to take moles of Na2SO4, and then I'm going to get to grams of Na2SO4. Okay. So what I need to do is I need to look at my periodic table again and take 2 times the molar mass of sodium, and that's 22.99 times 2. 1 sulfur, that would be 1 times 32.06. And then 4 oxygens, that's 16.00 times 4. These 3 elements, that is sodium, sulfur, and oxygen, all have 2 decimal places. So my rounded answer will have 2 decimal places. And that will be 142.04. Okay. This will enable me to cancel out the moles of sodium sulfate. Wait, I need a number in front of this moles of sodium sulfate, and that's a 1. And that's a definition. All right. I'm going to look at significant figures here. I got 3 significant figures. I have an infinite number of significant figures. I have 4 significant figures. Infinite, 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 and 5 significant figures. So the fewest number of significant figures I have is 3. So I'm going to plug this into my calculator and get a rounded number with 3 significant figures. So that will be 24.0, and the units are grams, and the formula is Na2SO4. So I'm going to circle that there like that. All right, fantastic. We are halfway done with the first part of this problem here. Okay, now the next thing that we need to do is we need to take the sulfuric acid and convert that into grams of sodium sulfate. So I actually have a number here for the sulfuric acid. Okay, and so we're going to use that value here. It's 12 milliliters. So I'm going to start off with 12.0 mils of H2SO4. That's what I'm starting off with here. Okay, wrote a little bit smaller because I do need to include one more step than on the previous one here. So I need a little bit more space. I know that. Okay. All right. So this right here, in order for me to cancel out mils of H2SO4, I need to have mils of H2SO4 in the denominator. Okay, and one of the biggest mistakes here is to use an incorrect concept, and that is I do not have this situation of 1 mole at STP. This problem does not say anything about STP, okay? And I do not have 1 mole. And so I cannot use this value of 22.414 liters. That is impossible. But what I do have is a density. I have a density of 1.84 grams per 1 milliliter of H2SO4. That enables me to cancel out the mils of H2SO4. Now I should be relatively home free conceptually. So right now I am starting off with grams of H2SO4, just like I started off with grams of sodium hydroxide, except I used the density to go from the volume to a mass using this density right here. All right. We've used density before. That was in the first unit of this whole entire year. All right, so now what we got to do is we're going to take this grams, and we're going to put that grams of H2SO4 in the denominator. And I am going to go from a mass to moles. That's mass to moles. using the molar mass and 1 mole. Hopefully that all makes sense. This is going to be moles of H2SO4. This number in front of the mole will be a 1, and this will be the molar mass for sulfuric acid. So that is 2 times 1.0079 plus 1 times 32.06 plus 4 times 16.00. And then sum that all up and then round it to 2 decimals. And that will be 98.08. That is the molar mass for sulfuric acid. So I'm going to cancel out grams of H2SO4 right there. Okay. I've done one more step here. Now I need to keep on going. Okay. In order for me to cancel out the moles of H2SO4, I need those moles of H2SO4 down here in this denominator term. Now is my opportunity to change the formula. So I'm going to say moles of whatever formula I want from the balanced equation, and that is the moles of the salt. That's Na2SO4. Okay. So where do these numbers come from? This mole ratio, they come from the balanced equation. For sulfuric acid, it's a 1. For sodium sulfate, it's a 1. So this is a 1, and this is a 1 right there like that. All right? This will enable me to cancel out moles of H2SO4. I have one more step. If this is moles of Na2SO4, I'm going to have moles of Na2SO4 down in the denominator term. Let me continue this just a little bit. And I want to get the mass. I am going from moles to mass using the molar mass. All right. So I actually already previously calculated the molar mass for sodium sulfate, and it's right up here at 142.04. That's grams Na2SO4. So that's the beautiful thing about these limiting reagent problems is you are going to end with the same units and the same formula. I'm canceling out moles of sodium sulfate. I need a 1 in front of the mole of that sodium sulfate. I'm looking at significant figures. I have 3 significant figures. I have 3 significant figures. That's infinite, infinite, 4 significant figures, infinite, 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 and 5 significant figures. So the fewest number of significant figures I have is 3. So I am going to take the 12 times 1.84 divided by 98.08 times 142.04. And I'm going to get the number with 3 significant figures of 32.0 grams of Na2SO4. Circle that. Okay, fantastic. So now I'm about halfway done with this entire problem. So I'm pretty excited about that, hopefully, Okay, and so let's see here. What do we got? What do we got is we need to figure out how much product is actually formed. And in order to do that, I need to compare these 2 numbers here that I circled in the black. Okay, which number am I going to use? I am going to use the number that's the smallest. So this number is actually my answer to this problem, and that is 24.0 grams of the salt. So that's the number that I'm going to use. The other number I'm going to cross out because one of the common mistakes is to actually sum up these 2 numbers since they have the same units and formula. We don't want to do that. So we're going to cross out the larger number. Okay. Now we need to figure out which is the limiting reagent and which is in excess. These are formulas. So from the smaller number, I'm going to go backwards and figure out what made that, and that is NaOH. So the limiting reagent is NaOH. So one of my answers is, what is the limiting reagent for the question? What is it? It's NaOH. And then the other formula, the other reactant is going to be in excess, just like the rock band. So H2SO4, sulfuric acid, is in excess. The limiting reagent is sodium hydroxide. The amount that is produced is 24.0 grams of salt, which is sodium sulfate. Okay. Now, I am still not quite done. So there's one more thing that I need to answer, and that is how many milliliters of unreacted reactant remains. So this is the one that is in excess. So I need to figure out how much of this remains. Okay. So what I need to do is do one more stoichiometric calculation here like this. Okay. And here's how this always works. You're always going to take the limiting reactant, which is on the reactant side, and you're going to take that and convert it to the other reactant. That is, the limiting reactant is going to be converted to the reactant that's in excess. So I'm going to have a whole monorail right here of that. Now, I will refer back to the numbers that are in here because we have already calculated all the molar masses that are required. So I'm going to slide this up so that we have actually the space in which to do this. Okay. And so here we go. So a fresh little start of stuff. So you're going to take the limiting reactant, which is the sodium hydroxide, and I have 13.5 grams of NaOH. Okay. And here we go. Going to take this. We're going to keep on going with this one. This is going to be a long train, but we're going to take the train all the way down to the station, baby. All right. So this is grams of sodium hydroxide. I will have grams of sodium hydroxide here. We have already previously calculated that. That is 40.00 grams of NaOH. That is equal to 1 mole of the same formula, NaOH. Okay. Again, ultimately, what I'm trying to do here is get to the other reactant. Now, I'm going to use a mole ratio. That's moles of NaOH to moles of H2SO4. Okay. This is a mole ratio, and this is the only time that you can change the formula. I'm looking at the stoichiometric coefficients on the balanced equation. A 1 in front of the sulfuric acid, 2 in front of the sodium hydroxide. Now I am going to go from moles of sulfuric acid to grams, and that's 1 mole of H2SO4. 2 grams, which is the molar mass. And again, we have already previously calculated the molar mass for sulfuric acid. That is 98.08 grams of H2SO4. The question is actually asking, what is the volume in milliliters that is unreacted? So I'm going to take this mass and using the density at 1.84 grams of H2SO4, and that's equal to 1 milliliter of H2SO4, right? You should see by this whole long calculation, the grams of sodium hydroxide cancel, moles of sodium hydroxide cancel, moles of sulfuric acid cancel, grams of sulfuric acid cancel, and I'm left with milliliters of sulfuric acid. I'm going to look at significant figures. There are 3 significant figures: infinite, 4, infinite, 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 4, infinite, and 3. So the fewest number of significant figures I have is 3. So I'm going to take 13.5 divided by 40.00 divided by 2 times 98.08 divided by 1.84. Round that to 3 significant figures, and I get 9.00 milliliters of H2SO4. So that is the amount of sulfuric acid that's required. So now what I need to do is I need to find out how much sulfuric acid did I have originally in this problem. So I'm going to look at this top of this problem, and I had 12 milliliters of sulfuric acid that was originally available to me in this problem. And I'm going to consume or use 9 milliliters. of H2SO4. Notice that I have my same units of milliliters, same formula of H2SO4, so I should be rocking and rolling with that. Okay. Now what we're going to do is we're going to do a subtraction, and we're going to get 3.0 milliliters of H2SO4 unreacted. Okay. And this is the part that remains. This is my other answer right there. Okay. Wow. That was a problem. That's a hard, difficult problem. It's a little bit more difficult. It's kind of stretching what we have done, and that's because it includes a density calculation in this, okay? And that's kind of an important thing for you to be able to do, because density is part of chemistry. Cool. All right, so I'm going to peel this away. Hopefully you followed everything along on this problem here. And ultimately, our answers are 24.0 grams of sodium sulfate. The limiting reagent is sodium hydroxide. The compound in excess is sulfuric acid, that's H2SO4. The amount of sulfuric acid required in this is 9 milliliters. So that is 9 milliliters will react with 13.5 grams of sodium hydroxide, and there'll be nothing left over. But it just so happens that we had 12 milliliters available to us. We used 9, and 3.0 milliliters of sulfuric acid remains unreacted. All right, let's peel this away, and let's do our last problem on this worksheet. Holy moly. Okay, here we go. Last problem. Let's see if we can knock this out here. Okay. All right. So just a little reminder here. I am the Crazy Hat Chemist. You can find me on YouTube. Please watch my videos on YouTube, and hopefully we'll answer all your chemistry needs. All right. So let's get moving on this one here. Our last problem here, it says an iron nail. So iron is Fe, and if it's a nail, that means it's solid. Okay, it's placed in a beaker of hydrochloric acid. That's a binary nonmetal acid, and that is a hydrogen with all acids, chloride ion, and that will give me my acid. It says a gas and a solution of ferric compound is formed. Okay, so I'm going to work with that information thus far and figure out what I've got going on here. So let's see here. We have iron, that's Fe, that's a solid, plus hydrochloric acid, that's HCl, that's aqueous. And these are my two reactants. Okay, this is a single displacement type of reaction. Iron is a metal, forms cations. It will displace the hydrogen. The hydrogen will now be by itself, and that is H2, and that is diatomic, and it is most certainly a gas. It says that a ferric compound is formed. Ferric is a 3+ charge. So that means that Fe and Cl3 is aqueous, is my product that is on the aqueous product that is formed. All right, now what I need to do is balance this. And it looks like I have 3 chlorines, 2 hydrogens, and I'm going to do a little magic here and say that I'm going to have a 2 in front of that right there. That will give me 3 in front of here. That will give me a 2 in front here and a 6 in front here. Okay, so a nice, wonderful balancing here of 2 in front of the iron, 6 in front of the hydrochloric acid, 3 in front of the hydrogen gas, and 2 in front of the ferric chloride. And now I got my balanced equation. All right. Now we're going to read on the problem, and it says 1.01 milliliters density 1.18 grams per mil. We just dealt with a density problem, so hopefully this isn't too bad, and I'm going to start off with that one. Of hydrochloric acid is used with a 0.28 gram iron nail. 0.15 grams of iron compound is recovered. So this compound is recovered. What is the percent yield and how many moles of unreacted reactant remains? So a lot to answer on this problem. This is as good as it gets. This is what you're going to get something like this on a test, or you should be able to answer all these questions here. So we're going to start off with our 1.01 milliliters. So 1.01 mils of the HCl. I'm going to draw my line here. I have quite a bit of information here to draw out because this is a density one. Okay, so what units belong down here? Milliliters. And it's the same formula, HCl. And the density is 1.18, and that's grams of HCl, and that's per milliliter, that's per 1 mil. This enables me to cancel out mils of HCl. Okay. What I need to do is I need to take this all the way to the ferric chloride, the ferric compound. So I'm taking the HCl all the way over to the ferric compound. By the way, this is another limiting reagent problem because I have numbers for both of the reactants. That tells me it's a limiting reagent. I have a number for a product. That means it's a percent yield problem in addition to that. All right. This is grams of HCl, so this is going to have to be grams of HCl up here, or sorry, down here in the denominator term in order for me to cancel these out. I'm using the flow chart. I'm going from grams to moles. It's going to be 1 mole. So this will be 1 mole of the same compound, HCl. Now I need to derive the molar mass of HCl, and that is going to be hydrogen at 1.0079 times 1, and chlorine at 35.453 times 1. The hydrogen has 4 decimal places. The chlorine has 3. So my final rounded molar mass is 36.461. That has 3 decimal places. 5 significant figures, but 3 decimal places. My next step here, after canceling out my grams of HCl, is to go from moles of HCl to moles of the ferric chloride compound, moles of FeCl3. Okay. Now, what I need to do is I need to use the mole ratio. So this is the mole ratio. I'm going to use the stoichiometric coefficients on the balanced equation. This will be a 6 in front of the HCl. This will be a 2 in front of the ferric chloride. That will enable me to cancel out moles of HCl. Now, in my denominator term right here, I will have moles of FeCl3. And I need to acquire the molar mass for ferric chloride. So that is going to be iron at 55.85 times 1, chlorine at 35.453 times 3, and I'm going to round this to 2 decimal places. That's going to be 162.21 grams of FeCl3. That's equal to 1 mole. Moles of ferric chloride cancels out, equals. I'm looking at significant figures. I have 3 significant figures, 3, infinite, 5, infinite, 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 and 5. So the fewest number of significant figures I have on this problem are 3. I'm going to plug this into my calculator. That's going to be 1.01 times 1.18 divided by 36.461 times 2 divided by 6 times 162.21. And I'm going to get the numeric value of 1.77, and the units are grams. The formula is FeCl3. I'm going to circle that. All right, fantastic. I've got one of them. Now I am going to take the 0.28 grams of iron nail. That's 0.28 grams of the solid iron nail. And I am going to do a similar thing and take this all the way to the same ending product of the ferric chloride. Okay, so let's see how we do this one here. All right, you're hanging on, I hope. Okay, so what we're going to do is we're going to get the molar mass. So we're going to go from grams to moles of the iron. And this is just looking on my periodic table and using 55.85. So that shouldn't be so bad. So 55.85, that's grams of Fe. That's equal to 1 mole of Fe. That will enable me to cancel out grams of Fe. And then that's where I'm at so far. All right, I'm going to have moles of Fe here, and then I am going to go to moles whatever I want. That's moles of the ferric chloride compound. And this is a mole ratio. This is the only time that you can change the formula. Notice I've changed the formula. I'm going to use the stoichiometric coefficients on the balanced equation. That for iron is a 2. That for ferric chloride is a 2. This will enable me to cancel out moles of iron. In the denominator of this next term, I will have moles of FeCl3. Now I'm going to go to mass of FeCl3. And I've already previously calculated the molar mass in the first step here. So that's 162.21 grams of FeCl3. That's equal to 1 mole. That enables me to cancel out the moles of ferric chloride. And then this will equal a number. I got two significant figures here, infinite, 4, infinite, infinite, 5, and infinite. So the fewest number of significant figures I have is 2. So in my calculator, I'm going to take 0.28 divided by 55.85 times 2 divided by 2 times 162.21, and I'm going to get the number 0.81 grams of FeCl3. I'm going to circle that. All right. Hopefully everybody's okay so far. Holding on. So now what we're going to do is we are going to compare these two numbers. I'm going to cross out the larger number so that I don't add it or do something silly with that. This is my answer of how much ferric chloride is produced. What is the limiting reagent? The limiting reagent is the one that made that smaller amount, which is iron. Which one is in excess? That is the hydrochloric acid. All right, so hopefully we've got that down. All right, now what we're going to do is we're going to answer our percent yield. So our percent yield is equal to the actual divided by the theoretical times 100. Okay, I'm going to move this up so you can see all of this. So what is the actual value? So I'm going to scroll this right back down here, and it says we have 0.15 grams of iron compound is recovered. That is this ferric chloride. So that is the actual amount that is given in this. So the actual amount is 0.15 grams of FeCl3. How much is the theoretical? That is this value here that's circled. That's 0.81 grams of FeCl3. I'm going to multiply this by 100. Okay, you should see here that I have the same units of grams, same formula of ferric chloride. This has two significant figures, this has two significant figures, and this 100 is infinite. So my percent yield will be 19% yield of FeCl3. And that is one of my other answers. It's not too bad. Well, it's a horrible percent yield, but it's a great answer. How about that? Okay, now we need to do one more thing here, and that is we're going to figure out how much of the reactant that is in excess, which is the hydrochloric acid, remains unreacted. So in order to do that, we're going to take our limiting reagent and we're going to start with that. And the limiting reagent is iron. So it's 0.28 grams of Fe. We're going to need a long train track, long monorail for this one here to carry on for this so that we can get it all. Okay, here we go. So we're going to take this limiting reagent and convert it to the other reactant, okay? And that's the HCl. We already have all the molar masses that we need already previously calculated. So this will be fast. 55.85 grams of Fe. That's equal to 1 mole of Fe. And then from there, we should be able to see that grams of Fe cancels out. And we're getting really close to the end of this. I'm so excited. Then moles of Fe are going to go to moles of HCl. And then I am going to use the stoichiometric coefficients from the balanced equation. So in front of the iron is a 2, and in front of the HCl is a 6, canceling out moles of Fe. Then here I will have moles of HCl, and I'm going to go to grams of HCl. So this is 1 mole of HCl and 36.461 grams. That's the molar mass of HCl. That will cancel out the moles of HCl. Then down over here, I am going to use the density, and that is 1.18 grams of HCl is equal to 1 milliliter of HCl. This is very similar to what we did on the previous problem. Grams of HCl cancels out, and I'm left with milliliters. So, number of significant figures, 2 significant figures, infinite, 4, infinite, 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 5, infinite, and 3. So the fewest number of significant figures I have is 2. That's the number I'm working with. And then I'm going to type into my calculator the following. 0.28 divided by 55.85 times 6 divided by 2 times 36.461 divided by 1.18. And then I'm going to round that to 2 significant figures. That will be 0.46 milliliters of HCl. All right. So now we're going to scroll this right up here, and we're going to say, well, how much HCl was available to me in terms of milliliters? 1.01 milliliters of HCl was available. How much did I use? 0.46 milliliters of HCl was consumed. We're going to draw a line in the sand here, and we are going to subtract these two numbers, and we will get the following: 0.55 milliliters of HCl in excess that is unreacted. And that is our final answer there. So we've got 5 answers on this. We've got 0. So I'm going to zoom on out of here so you can see all of this, because there's a lot of work on this. Okay, we have our answer of how much of the ferric chloride compound is produced, 0.81 grams. What's the limiting reagent? Fe, that's iron. What reagent is in excess? That's HCl. What's the percent yield? 19% yield of the ferric chloride compound. And how much of the excess reagent is unreacted in excess? And that's 0.55 milliliters of HCl. Wow. That was a problem. You should be able to do that. Make sure that you go over that again. That's a fantastic problem. Again, I am the Crazy Hat Chemist. Please subscribe to my YouTube channel. Give me a thumbs up. Hopefully you enjoyed that presentation. And there's one more worksheet that we have to do, and that's stoichiometry worksheet number 3. So hang on for that one. I'll see you next time. Talk to you later. Bye now.